Then we're just gonna. So they're just gonna finish the integral part, I guess, altogether by just doing this Leibniz formula. It's similar to the the Euler formula that he just mentioned, and you sometimes might use it, sometimes it has nothing to do with how to solve problems. Now, just one disclaimer, you can be used in multiple cases. Just because it can, it doesn't mean it's recommended. I'll give an example once we write it down. So we're gonna start with. I need to know. Okay. Okay. The idea is, it's a theorem for taking a derivative of an integral. But what type of integral? Integral type A of t, B of t, f x t dt. No, dx sorry. Yeah. Or yeah. Well, what's the idea here? Suppose you had something like integral of, and I'm going to create something right now, t to t squared of tx squared plus t dx. Okay, suppose you have something like this where t is just a variable. The idea is that in this integral, I told you several times, this dx tells you what you are integrating over. So when you're asked to compute this derivative of t squared, tx squared plus t dx with respect to t, again, with respect to t, then if you didn't know this Leibniz rule, what you were supposed to do is just probably compute this integral, see what the value is, and then take a derivative of it. Okay? Sometimes the problem is that computing that integral might be very hard, impossible, all of the above. Okay? So this just comes in and basically gives you another trick that you can use. Now, I'm going to emphasize again, the derivative, this thing is dx. Okay, it's really, really important. This is dx. And just so we're clear about it, if we take a derivative of this thing, tx squared plus t dx, but we take a derivative with respect to x, then it's fine, okay? But then you're just stuck with the primitive thing. This is different. So just distinguish between these two. Okay. Leibniz talks about this. This would just be the definition of the integral because we have dx here. So just wanted to emphasize that. Now, the rule itself is rather long, I would say. So I think for your sake, I think it comes in the cheat sheet that you get on the exam. I hope it does at least. Right, so this is it, and we have to compute d of dt. What is this equal to? And one way to memorize it is how do we write? We use f of b minus f of a, I think. We use in my head again. Let's write the formula actually. I'll write the formula right in front, and then I'll basically give you some intuition of how I memorize it. Kind of deducted, but I assume the memorization works as well. So it's you just evaluate this f at b t instead of x, and then take a derivative of this b t with respect to t. Okay. Then you put f(a)t here again instead of x(t), and you take a derivative of a(t) dt, and then plus you just add the naive integral to it. Okay, what do I mean the naive derivation? Just integral a(t) dt, derivative of f(xt), derivative of t dx. Okay, and I know it looks kind of ugly, but it's really not that hard to apply if you have it. The way I tend to memorize it is, remember the integral, the value of it was usually just some integral from a to b of something. Dx was equal to f of b minus f of a. Okay, this is how we define the definite integral. The way I memorize it, I'm like, okay, this is some sort of f of b. This is some sort of f of a. I'll put approximate, whatever. That's just how I memorize it. If this doesn't work for you and it's more confusing, then find your own way. And this is just naive derivation. Okay, so this is kind of how I memorize it. I don't know if it works for you guys. Again, this is how I try to keep track of it. Now, it might look really, really ugly, but it's actually not that bad. Let's take an example. Let's take the integral that I gave initially and see if we can evaluate this. So the one I took initially was, I wanted to compute derivative with respect to dt of integral t squared tx squared plus t dx. Okay, this is what I want to compute. And the way to start, at least when you're applying it, I would just identify all the elements. So what do I mean by that? This is my a of t, this is my b of t, this is obviously my f of x. So I need to compute, let's put it like this, would be something here minus something here plus something here. Okay, and now let's see what those somethings are. The first term here was this f of dt times t, t times derivative dt t. So now we just literally replace. So we get, instead of x, I'm going to use bt. So I get, again, my f of xt is just tx squared plus t. My bt, this is what I would call just identification, basically just writing everything I know down, so it makes my life easier, I guess, when I plug in values. So I get this f of t squared t times derivative t squared derivative of t. Everyone follow up to this replacement that I did right here? I just replaced this b of t with t squared from here. Right? First thing I did. Now, second thing, I'm just going to write the function out. If this is f of xt, then this value is just t times t squared plus t times this derivative. Everyone follow on that? So again, I want to take this derivative. I don't know, for some reason the problem asked me to take this derivative. And I just remember that it's 3 parts, 1, 2, 3. And now I just pull out my scrap paper or whatever, and I start identifying stuff and trying to see where I'm at. I just noticed that according to the definition, this is a of t, this is b of t, and this is my f of xt. Right, just according to the definition. So I write that stuff down right here, I copy it here. And I remember that the first term of the derivation is this thing. And I just replace slowly everything in. That is my logic. I first replace this v of t, which is t squared. I put it everywhere, and then I replace my f with this value. And I get this. Everything on board with that? Okay, now I just take this. This is my first term, so I just take it and put it here. And I get, I'm not gonna touch it, I guess that much. T4 plus t times, and we're just gonna compute what's the derivative of t squared with respect to t. It's just 2t. Okay, first term done. Second term. What is my second term? My second term is f a t times derivative of a t derivative. Okay. Again, remember a t is just t. Well, I think I put it. Yeah, a t is just t, and then f of a t, f of x t is just. I think I put it tx squared plus t. All right, so again, I do all the replacements. First, I put in a of t. So I get f of t times derivative of t with respect to t. This is just equal to t squared plus t derivative of t with respect to t. All right, literally just plugging the values. So now I have this term over here, which is my second one, and I'm just going to plug it in here. So I get t to the third plus t times what's the derivative of t with respect to t? Just 1. Okay? Second term done. And now for the third term is the last one. My third term is integral at b of t derivative f x t dt dx. So again, b of t is equal to t squared, a of t is equal to t, f of xt is equal to t squared. It's equal to tx squared plus t, tx squared plus t. Okay, I haven't had it written up top. So now I just write this out, and this is equal to integral from t to t squared, derivative of tx squared plus t with respect to t dx is just equal to integral t squared x, what's this derivative, x squared plus 1 dx. And this is my final term. And now I can just take this final term, plug it in here, and I'm done. I just get, this is integral t squared x squared plus 1 dx. Okay, and this is how I applied my Leibniz formula to this function. Okay, any questions on how I applied it or everything? Now, I think I have to answer a couple of questions. Like, first one being, why would you ever want to do that? And the reason being is that I took in this case a really simple example. So you could have just computed this integral, right? You could have just computed this integral tx squared plus t dx. You could have just computed it. So let's just do that. And what's the integral from t to t squared of I said tx squared plus t dt. And what is this? This is just dx, sorry, dx. Again, really important, dx. Okay, this is just integral t squared t x squared plus 1 dx, which is just equal to t is a constant in dx. Dx is a variable, t is a constant here. So I put it out in front. T t squared, x squared plus 1 dx, and you guys should know this. This is just t times x to the third over 3 plus x evaluated from t squared. And this just gives me some value that I'm not really interested in computing on. I guess I'll do it. T to the 6 over 3 plus t squared. Again, I'm just plugging in values. You don't really need to pay attention to this. This is just me basically giving the final answer. Minus t. Okay, you get this thing, and then you can say, oh, they wanted me to compute the derivative of this. Fine, I'll just take derivative of this thing with respect to t, and I get the answer without applying your Leibniz formula, right? Because remember, initially I was asking you to compute the derivative of this thing with respect to t, and now you just said I don't want to apply your Leibniz formula, so I'm just going to compute it. And this formula is actually really nice. The polynomial, right? It's easy to take a derivative of, so everything's fine. The problem is sometimes I gave an easy function here, but sometimes I might give an extremely ugly function there, which you might not be able to compute the derivative of, the integral of. Like for example, if I gave something like integral from t squared, we still keep this because I kind of like it. I would give e to the power of x to the power of log of t times t to the power of ln x t, okay, dx. Now, if I give you this one, do you want to integrate this one? I would suggest not, okay? So in these examples, the Leibniz formula comes really into play when you can't compute the integral itself. And I'm actually gonna, so you can even apply it on the homework, on one of the improper derivatives. Now, that is not really the way it's supposed to be done, but it is a way in which it's supposed to be done, in which it can be done, okay? I'm talking here about, I don't know if you've reached it, but I can mention it doesn't matter. On problem, I think D, you're asked to compute some df of df with respect to a or something like that. This is something that you need to compute. dm, I think it is, or m is like some f function, and the idea is in this case that you're going to have to compute derivative of an integral of that ugly thing fs ds, I don't know where it is here, with respect to a. So this would look like a classic application of Leibniz, especially because you can't compute this integral. They tell you specifically in the problem, do not attempt to compute this integral. So in this case, Leibniz basically offers you a shortcut of, I'm not going to compute this integral, but I'm still going to compute the derivative, if that makes sense. Okay? Now, is this the way to solve the problem? Not really. I mean, you can solve it easier, but it's a great application, okay? It's a great application. The only reason that you don't need to apply Leibniz to this case is because the f function is really nice in your homework. If the f function was uglier, you needed to apply Leibniz in this case. So that's how strong it is. Now, I guess you can do another example of Leibniz, and then I'm gonna show you. I'm gonna show you, I guess, what double integrals are. Only to show you guys, just so you know, it's probably gonna be like a 5-minute intro into double integrals. Not much, because there's not much to say there. And then we're probably gonna do another exam problem or something like that. That's gonna be it. Cool. Let's take another example from Leibniz. Let's see if I actually have some examples. I can create some ugly functions, but that will not serve any purpose. So, you can take an easy example. It doesn't have to be ugly, right? It's your first application, so why take it ugly? You can just train yourself, right? You can just create yourself all your functions however you want. It doesn't matter. So the one I'm going to ask you to evaluate is, let's do a twist. 1 to t of x e t dx. Well, I know again, this is really simple just to test the application of it. You could compute this integral and take a derivative of it. I'm asking you to compute the derivative of this integral with respect to t. What is this equal to? And yes, I know you can compute this integral and it looks nice. Just don't do it. Pretend you can't compute it. Pretend you haven't learned how to compute those integrals. Okay? Unless you want me to give you something like this to take a derivative of. Just let me know. If you're excited, I can do that. So again, we're just literally gonna use the Leibniz. Unsurprisingly, I said use the Leibniz. So what was I supposed to do? We're gonna use this one, and I'm gonna tell you what I mean by a twist. Let's do it on the other page. This one. So again, the way I would start it, especially since I'm new to this Leibniz thing, you write the derivative of 1 e x e t dx. This is derivative with respect to t, and you know it's equal to 1 minus second part plus third part. Okay, and we just start doing it. I can't say anything more than that. So the first part is your f b t, t times derivative of bt. Also, I'm just splitting it this way because I think it's easier for you guys to observe what I'm doing. I could have just replaced it instantly, all three of them if you want, but I think this is more helpful. Okay, so we have this again. We evaluate our b, a, and whatever. Looking at my function here, this is a of t, and this is important because this a of t and b of t can just be constant. Okay, that is really important. And in the case of constants, everything's gonna work out really nicely. So, and I'll give you like a lemma. I don't know. It's a strong name for it, but I'll give you a result that you can use and basically apply Leibniz faster in some cases. Okay, so you have this. As I said, my f of xt is equal to what was it? Xet, and bt is equal to t. So this is equal again. Hopefully you guys got the idea of what I'm doing. So I'm just gonna, accelerate, I guess, a little bit. This thing is just gonna be the b of t replaces t. And this is just gonna be t et times derivative of t with respect to t. And again, this is done. This is derivative, and this is just 1. So my first term is just t e to the power of t. Now, I keep this paper because I'm going to use it. I write the second term. Second term, f a t, t, derivative of a t, derivative of t, f x t. By the way, on an exam, if you are on an exam and you are applying this Leibniz thing by any chance, I don't need to see all these like 1, 2 thingies. You can just literally write the result here. Okay, like there's no need for you to give me all these steps. I'm writing all these steps for you because it's first lecture on this. But on the exam, if you just gave me this, the one we just solved. If you just, on the exam, if you just said, I'm applying Leibniz, and you get this thing over here, then that's maximum point. Like, I don't need to see anything else. Okay? Like if you just write this, then it's maximum points for me. I don't need to see anything else. I'm just going through the identification process for you guys. Okay. So A of t is 1. So this would just be f1t derivative of 1 derivative of t. Okay, and this is where I said the twist comes in. What is this derivative? It's just 0. Okay, it's a constant taking derivative with respect to t. This is 0, so this whole thing is 0. I don't even need to replace f inside of it. So my second term is just 0. Okay? Again, the logic was that in this case, my AT is 1. Okay, it's 1 here. I don't have a color on it, but that's a 1. So that's my AT. My AT is a constant. So when I just apply the formula for the second term, I'm going to get derivative of AT with respect to t, which is just derivative of 1 with respect to t. That's 0. Okay, and that's why my second term is all 0. And now the third term was just a naive integral AT dt derivative of f of xt derivative of t dx. This is just integral of 1 t x e t derivative of t dx, and unfortunately then it simplified the same thing, but that's fine. Okay, so this is my last term. This is my last term. I take it from here, and I take it from here, and I plug it. Okay, and I'm done. Obviously now, if I wanted to be thorough and push it towards the end, I could compute this thing until the end. Okay, I can compute that because this is a constant. So it's just, sure, we can do that, I guess. So the final answer that I would give is this derivative of 1 t, integral of 1 t x e t d x over dt is just equal to t e t plus integral. I said the e of t is a constant because I'm taking the derivative of x dx. So this is just equal to t e t x plus x squared over 2 between 1 and t. So this is just e t plus e t squared over 2 minus e of t over 2. Okay, pretty standard, doesn't do anything special. Now, the reason I told you about this trick, or what I wanted to emphasize, is if you see constants here, it means that when you take a derivative, it all just goes, those elements just go away. Okay, let's keep in mind the definition. In the definition, I have to take a derivative of b of t, so the edges, and a of t. Okay, so one particular case, one fast case that I can give you is if you're asked, if your function looks like this, integral of constant 1 and constant 2 of f x t dt, x, sorry about that. Okay, if it looks like this, okay, if you have constant 1 to constant 2. So for example, if I just have from integral from 0 to 1 of whatever ugly function you can create here, log of t x t, okay, dx, then when I want to compute the derivative of this, with respect to t, if you look at the formula here, again, have in mind the formula. I have this derivative b of t. This in my case is going to be 0 because this is a constant. 1 and 0 are constant. So, and the same applies for this one. So my answer is actually going to be pretty simple. I'm going to get, remember three terms, minus, plus the last term. In my case, I'm just going to get 0 minus 0 plus just the integral of what's inside. So plus integral 0, 1 of derivative log of t xt derivative of t dx. Everyone follow on the logic and why. In the case that I have constants here, any numbers that don't depend on t, when I apply Leibniz, I can just do this naive integral and it works out. Okay? The reason being, again, why is this 0? Because in the formula, I would have to put here a d b t derivative of t, which in my case, this is b of t, this is a of t. So in my case, it would just be 1 dt, which is 0. And in this case, it would be derivative of at, derivative of t, derivative of 0 dt. This is again 0. Does everyone understand now why those two terms just become 0 when I have constant edges or margins of integration? So I would think that in the vast majority of the cases, this is the Leibniz you are going to apply. But again, who knows? This is just, I would say, the more practical version of it. But you know, this is where it comes from. This is the original thing. Now, for the remainder of 10 minutes, I just want to briefly cover what a double integral looks like and what it means. I've seen it in previous years. I've not emphasized it, so I'm just gonna give you like a short intro. The intro that I want to talk about is something like this. What if I have integral of xy dx dy? What if I have something like this? Yeah. In what sense? No. Do not do that. No, that is not okay. No, what you can do here is just compute it one at a time. What do I mean by this? I can have here 10 integrals, it doesn't matter. The way you solve them is just go around and just look. I just compute this integral first. I'm literally just computing that one. I don't care about anything that's happening anywhere else. I'm literally just computing this one. Now, in this case, what is y? Y is just a constant in this particular integral that I highlighted. So, do you guys agree that this integral is just equal to x squared over 2 times y? Okay, everyone convinced? That just the thing that I highlighted, whatever. So then I just copy the remaining terms. This is integral dy. And now the same logic applies. X is a constant here. I mean, yeah, x is a constant because I'm integrating over dy. So this is just equal to x squared, constant. I mean, this is a constant times y squared over 2. So realistically, these double integrals are nothing but just normal integrals computed one after each other, if that makes sense. We can take another short example. Yes. Integral of ex y to the power of 3 plus x y. Sure, I can't remember. X squared. Fine. Dx dy. Again, what do we do here? We just solve the inner integral and then move outside. Okay, that is the process. The process is, I don't care about what's happening. I just look at this integral. I look at this integral, and in this case, I'm integrating over dx. That's why I've always emphasized that these dx's are really, really important. I'm dx, so y is a constant, so this is just e to the x, y third, plus x to the 3 over 3 y. Okay? Okay, and now I just, seems correct, and now I just put in the other integral dy, and again, x is constant, so I just slap it in. Ex, no integral y4 4 plus x 3 over 2 y squared. So again, I'm not really expecting, I guess, for double integrals to be on the exam, but I don't know what's happening this year. So in this case, you're just prepared. This is literally all the prep I can give you for double integrals. You just solve them from inside out as normal integrals. Okay, so I'll actually write that. If you get it, at least I know I did my job on that one. So how to solve double, triple, whatever. It can be whatever. I can give you n integrals. Okay. Integrals. So from the inside out as normal integrals. Okay, this is the standard procedure. And as you can see, it's not really hard. It might be a little bit confusing when you have limits of integration. I guess we could do an example of that. A trickier example of that. Let's see what it is. Yes. Yeah. That's exactly what I was gonna do right now. Yeah, so the question that I was gonna think, I'll do one of them. It's exactly the same way. I stick to the thing I said here. You solve from the inside out as normal integrals. What do I mean by that? Let's take a trickier one. I don't know. So 0 to 1, and then I'll take 1 to y. So that looks about right. And then let's take some creative integral here. I actually like the previous one. So yeah, let's use the previous one actually. Okay, that's x squared y dx dy. Okay. It doesn't matter if they are it doesn't matter if the value, if it's a definite integral again, because I'm just gonna stick to my procedure, which is solve from the inside out. So isolate this one, solve it. Let's see what is equal to. It's again the primitive, which we computed previously, ex y third plus x to the third over 3 y. Okay, and you evaluate this from 1 to y. Now, this is, I guess, the only case where it can be a little bit tricky. What do you replace here from 1 to y? What is the value that you're like doing from 1 to y? So that's why, again, keep in mind what you just did. The x. Okay? I am doing x from 1 to y. Okay, it's literally just like solving this. If this is confusing for you guys, you can just take this out and say I'm solving this one and then put it back in. Okay? And this is just integral from 0 to 1 of this whole thing, dy. All right, solve inside out. Any questions on this, on the procedure? You can just take this integral out, this one that you can see here, solve it, and then plug it back in. It's the same thing. Okay? Now this is just equal to 0, 1, And as I said, I'm going to plug y. So I get e to the y to the third, plus, should give it something easier, I guess. Okay, minus e to the power of 1, y third, plus 1 over 3, y, everything dy. And yeah, you just do this thing and it works out. This is just a normal integral. Yeah, let's see if I can do some splitting past here. So I show you. And again, now you're just stuck with this is a regular integral that you could get on the example. This is just a one variable integral, 0 to 1, only y inside, no x's, clean integral that you can solve. Okay, so the double integrals are nothing but just an integral, basically saying I'm computing the integral of an integral. That's kind of it. Okay. Any questions on this, on how to solve double integrals, at least conceptually? Is everyone clear on conceptually how you would solve them? Okay. Then I think this is a good time for break. Let's do like a 10-15 minute break, and then we're going to do some exam problems again. Yeah. Okay. So this is how we learn the definition of the integral, right? I told you, remember the whole drawing with I go from f of t by integration to big F of t, and by derivation I go back. Remember, I think I did something like this, like yin yang, all that stuff. Yeah. Well, so keep in mind, whenever you can take advantage of this thing, it's so strong, because if I want to find P and Q such that this thing is equal to this thing, then I'm just saying, oh, okay, then it means that the derivative of T E Q plus ln of T, basically the right hand side plus the constant, derivative with respect to T must give me what's underneath the integral, plus the P because it's a constant. P T E minus 1 ln of this ugly thing, T E minus 1. You guys understand logic? I just took advantage of the fact that they gave me the final form, and they never said integrate the left side. So I'm just using the fact that integration is the opposite of derivation. So if they asked me to check or to find P and Q such that the left side is equal to the right side, it's the same as taking the derivative of the right hand side and checking that it's the integral thing. Okay, so that's exactly what I'm going to do right now. Take a derivative of this and see where I'm at. So take a derivative of this and I get T E times E minus 1 times E Q plus log of T plus T, I use the chain rule here, times 1 over T plus constant. Looks about right. Plus constant. No constant, sorry. Derivative, I think the derivative of the constant is 0. Sorry about that. Wrong, big mistake on my side. T E minus 1 log of E squared T E minus 1. Okay? And this is much easier than computing that integral. It's just faster, just saves time. Now I take derivative of T, I can simplify this T minus 1, goes away. And what I have left is actually just E Q plus E ln of T plus 1 is equal to E ln E squared T E minus 1. And I know this doesn't really look like they're equal, kind of at all, to be honest. So let's just apply the log rules again to this. Is equal to E, and again, I do the same transformations I did before, and I get 2 ln of E plus E minus 1 ln of T. Okay, and now open the parentheses, and what do we get? We get EQ plus E ln of T plus 1 is equal to 2P plus P E minus 1 ln of T. Okay, now the coefficients for ln of T have to be equal, so this thing has to be equal to this thing. And then okay, so how I just identify my terms. This thing has to be equal to the corresponding term for log of T on the right, on the other side. And everything else has to be equal. So this plus this has to be equal to 2P. Okay, maybe I can rewrite it. So from this, I just get that P E minus 1 is equal to E. And then I get that the other stuff, EQ plus 1 has to be equal to 2P. Okay, I just made everything equal. So from here, I get P is equal to E over E minus 1. And then EQ plus 1 is equal to 2 E minus 1. So Q is just equal to whatever this thing is. E minus 1 minus 1 and 1 over E or something. I don't know. I probably can look nicer, but I don't care that much for now. Well, and I'm done. And this is going to be much faster than computing these derivatives over here, or these integrals over here. So what I wanted to show you is if you get a problem like find PQ such that this is equal to that, you don't need to compute it. You can just take a derivative of the other side and make it equal. That is basically one method I wanted to show you guys. Okay. So again, you could have done it this way. This is 100% solvable, but this is probably another 7 to 8 lines of good writing. A lot of mistakes can pop up in those lines. This is much direct. I take derivative. Oh, here. This proof is literally 1, 2, 3, 4, 5, 6 lines. Okay, so it's not that bad. Now I agree, a lot of mistakes can come up here, but definitely less than if you do it the other side. So this is what I would recommend. If they don't say proved by anti-differentiation, in which case they'll even put in parentheses. If you take a derivative, you get 0 points. You can take advantage of that. If it's a mistake on the side of the professor or who makes the problems, take advantage of that. It's 3 points. Just take a derivative, make it equal. All right, so this is what I want to show you. This is taking advantage of the derivative. And now I think we're up to the problem that we left last time. We didn't really do. And I said, and you promised me that if I let you guys go 5 minutes early, we're going to think about it. So I'm expecting ideas here because I haven't thought about it. And I don't know how to solve it. So let's go. Ideas here. The hint says use substitution first. So what substitution are we going to use here? Any ideas what of the substitution we're going to use? Yeah, there's literally one term here that we can substitute, right? It's only this that we can substitute. So I just give it a shot. U is equal to square root of z. Du is equal to just give it a second. My derivatives sometimes just stop. I don't know why. Okay. Great. So again, for substitution, my substitution taking care of du dz, now taking care of the margins. If z is equal to 1, then u is equal to square root of 1, which is 1. If z is equal to x, then u is equal to square root of x, which is just square root of x. Okay, now we replace our values. This is equal to integral 1 square root of x. E to the u dz. Great. We're almost there. What's the problem now? Remember, dz u back. I want to have du here. Okay. I can't integrate apples over tomatoes. Okay, think of it like that. It's actually it should make sense. So now I'm just literally struggling to create this d of u here. So I look at this equation over here. Okay. From this equation, I can just get d of z is equal to du times 2 square root of z. Everyone on board with it? Okay. I just flipped everything. I left dz here alone. So, okay, but I still have a problem because I'm going to have du dz here at the same time. Now, square root of z is equal to u. That's the whole trick. That's the whole idea. So this is just equal to du times 2u. Okay. So now I can plug this new replacement or whatever, this new notation. I can plug it into my integral. So I get integral of 1 square root of x e to the u times 2u du. Okay? Yes.
What you put x equal to like the square root of x after.
So when you're dealing with definite integrals, there are two parts. There's this part, the first part, which is specific to all integrals with substitution, and then it's adapting the margins. So since my change of variables is square root of z, and I was integrating z from 1 to x, now when I integrate u, I can't integrate from 1 to x. I'm going to integrate from 1 to square root of x.
Okay.
Okay. So I need to adapt my limits of integration, but very good question. Okay. Anything else? Yes. Where? Oh, it's a D. So I just make it curly. No, it's a D. It's no, yeah. Usually you should think of the derivative of like the derivative having sense over if I write it under like a fraction, like du over something. Then realistically, if I've seen even people writing it. Okay, so technically in an isomorphic space, they're the same thing. But to answer the question simply, yes, it's just a d. Good. Cool. So now we're stuck with this integral. 2, 1 square root of x u times e of u. Now, does this integral look familiar to you? I think we solved it in class like 4 times already. As you can see, I guess, that all the integral problems just are wrapped in some nice thing, but they all converge to some sort of problem that we've solved in this class. The question is, can you get to that point? Okay? Because this one we solved, I think it was the first integral. what, and we decided on, and I even gave you the rule, whenever you have this one, you want to take the underivative part. So this one, no derivative, let's put it, no derivative A, and this being the B prime. Okay? If we use the rule AB is equal to integral A prime B plus integral A B prime. Okay? This is the rule I've given to you. I think we did it with U and V, but now I have U here, so I can't really do the same rule. But we're gonna do this by part. This is the first example that we learned the by parts, and it's completely standard. Yes. Yes, that I did use the D. Yes, there is a D there. Yeah, I didn't write any D because it doesn't matter. But yeah, I lost. Yeah, okay. Okay. So now let's get into our standard by part setting, okay? You remember we had to choose our, what is the derivative part, what is the non-derivative part, and I use that as a rule. Always take the polynomial next to the exponential without derivative. No derivative. This was the rule. I think I even said it as a rule. No derivative, and then I take B prime as being EU. Okay, so now I have to compute A prime, which is just 1, and then B is just integral of EU du, which is just EU. So I have my A's, my B prime, my A prime, and I have my B again. So at this point, I can use the formula. Well, the formula was AB integral A prime B plus integral A B prime. So let's see it. A is U times E of U. Now, in this case, remember, it's a definite integral, so I have to integrate this between 1 square root of x is equal to integral of what's A prime derivative? 1 times B e to the power of du, plus again, keep the heads of integration, plus integral 1 square root of x. My A is U times B prime is EU du. Now, what do you notice? This is the integral where I started. Okay? This is the same one as here. So I applied it correctly. Now, on the left-hand side, I have nothing to do, and this integral right here is very simple. It's just e to the power of u du. So my integral is just equal to integral of 1 square root of x of, I don't know what I'm writing here. I think I'm losing my head. So it's this one is equal to u EU from 1 to square root of x minus integral 1 square root of x e to the u du, which looks really nice. So integral square root of x u e to the u du is equal to, plug in the numbers, square root of x e square root of x minus 1 times e to the power of 1 minus this integral, which is just e to the u from 1 to square root of x. So this is just 1 square root of x u EU du is equal to square root of x e to the square root of x minus e minus parentheses e square root of x minus e to the 1. Okay. Did I make a mistake?
This one with the 2.
Oh, forgot the 2. Yeah, of course I forgot the 2. Yeah. Yeah, of course. It's this 2 that they're talking about. This 2 over here. Yeah, of course I did. So if I computed this thing as being equal to this, then 2 times this thing is equal to 2 times this whole thing. Yeah, thanks. As you can see, mistakes like this happens to the best of us. I would have probably gotten 9 out of 10 for this one. Something like that, maybe. Depends on the grader it's feeling. Okay. Any questions on what I did here? No? Nothing? Okay. So again, I think we've done in class literally all the integrals, all the types of integrals that you can get. It's just a matter of you getting to the point, seeing that integral for what it truly is. Like, for example, if I gave you the integral initially, which I don't want to disappear again. Oh, sure. If I gave you this integral right here, most of you wouldn't have guessed that, hey, this integral is just gonna become the first integral that I ever solved, right? But if you just apply a substitution to it, it literally just becomes one of the easiest ones you can get. Standard by far. That's, I guess, all the problems are just like that. You just gotta keep your calm and do your thing. Now, we're gonna do some limits. I know this is integration class, but I think everyone knows integration by now. Easily, hopefully. I don't know, maybe. So, and we have like 19 minutes. So I'd rather just spend them in doing these two limits over here. Okay? I think everyone could use the exercise, no offense. Limit when x goes to 0 with a plus ln of x squared e squared of x minus e minus square root of x, and then the other one, limit x goes to infinity okay. And before you hit me with I'm proficient at these integrals, and I don't at these limits, I don't need to do limits. If you like, you don't need to tell me, but if you have done these integrals in less than 10 seconds each, then I believe you, and I apologize for giving you limits. Otherwise, I think you still need some practice on limits. Okay, so I won't give you like 10 seconds, but I'll give you like 3 minutes to do both of them. We're gonna copy them. I'll maybe look for something else. We had a good problem there. It's hard to find the policy guys, because you just solve them all. Okay. Where we at? Did we finish it all? Now, disclaimer, if you wrote more than, I don't know, 4 lines, we probably made a mistake already. So what's the first thing we do with a limit? First thing. We evaluate it. No, we don't apply what top. We evaluate it first and see what we're at. So I'm just gonna evaluate it here. I don't need to write anything. When x goes to 0, square root of x goes to 0. E to the 0 goes to 1. Square root of x goes to 0, e to the 0 goes to 1. 1 minus 1, 0. Okay? What does log of x go when x goes to 0? Minus infinity. Squared? Infinity. So my case is infinity over 0, which is equal to infinity. First problem done. Now, second problem. X goes to infinity, x goes to infinity. Log of x goes to infinity. X to the 1 over n, 1 over infinity, because it's 1 over xn, so it's 1 over infinity. And this thing, infinity. So what's my case right now? I have infinity times infinity, which is truly infinity. And then below I have 1 over infinity times infinity. So I'm kind of messed up. I have no idea what to do here. One idea is, I don't know if you want to keep this in mind for me, but I hate working with minuses and 1 over n next to the minus n and all those stuff. They're just too ugly for me. I'm not good enough for that stuff. So what I do is just multiply the fraction. I think they put it in the other side by xn. So I just get limit x infinity xn times x ln of x xn times x minus n ex over n. Okay, now why did I do that? Let's evaluate again. This goes away. So I have infinity, I have this x, which goes to infinity, n is a number, doesn't matter. So this goes to infinity, so e goes to infinity. Good. Now, xn infinity, infinity, infinity. So I have an infinity over infinity case. Okay? Now, 2 possibilities. 1, apply L'Hopital. Eventually, you're going to get an answer. Eventually. I would say it's going to take a while. So, first one, L'Hopital. Second one, exponential, bigger, any power. So, if I use this thing, because I'm lazy and I noticed this, I remember this thing, I just get 0. Because this one, the claim is that this thing much bigger than everything up top. Okay? And I'm done in 3 lines. I could have done this 2 lines. Okay? Honestly, how many of you have applied L'Hopital the first one? Like, you don't need to raise your hand and tell me, but just think about it. Like, how many of you have applied L'Hopital the first one? Or how many of you have realized that after you evaluate, it's basically just, this is your answer. It's just a matter of like evaluating and then taking the simple way out. I'm actually going to write some things here. Let's see what the time is. Yeah, I'll actually write some log things. I've seen a lot of people having a lot of troubles with this. So I'll write it as a disclaimer here. All I write here is at the limit. Okay. I don't want you to go to some professor and be like, this guy's insane. Limit of 0, ln of 0 does not exist. Well, it doesn't, but I'm just writing it for you guys. Ln of 0 goes to minus infinity. Ln of 0 of 1 is equal to 0. No limit is equal to 0. E to the 0 is equal to 1. And then e to the minus infinity is just 1 over E infinity, which is just 0. Right. I'm just writing this because I noticed a lot of people having trouble with this, and unfortunately, it's just how it is. If you mess one of these up and you use them in your evaluation, your whole problem falls apart. So that's why it's I don't know. It's good to kind of memorize them. Anyway, now I found you a beautiful problem. Sorry?
So what is, no, yeah, so, I don't know.
ln of 0? ln of 1? Yeah, that's supposed to be a 1, sorry for that. This is equal to ln of 1. Sorry for that. I wrote 0 initially, but that's a 1. Alright. This is equal to e to the 0 is equal to 1, exactly 1. This obviously this is taking out the limit, right? E to the minus infinity is not this. Infinity is not a number. Okay, just to be sure. Cool. Now let's do a beautiful integral for you guys. And now it's clear that it says show by anti-differentiation. It is mandatory to integrate. There is no score for differentiating the right-hand side. Unless you see something like that, feel free to always take a derivative of it. It's going to make your life much easier. If they miss that, you're lucky. What can I say? So in this case, they come up onto you guys, and they don't want to let you guys take a derivative. They want you to integrate. So, integrate. Now, I'm not going to copy the answer. It's there. So I need to integrate this thing. How many of you, when you see this problem, just panic and say, I'm not doing that, I'm going last, I'm going to do something else first? Well, a lot of you, yes, I know, I would have done the same. But I would recommend, before skipping the integral problem, because they're usually pretty easy, just take a minute to see if you have any idea on how to do it, or it looks like something we've done. Does it look like something we've done in class? Because again, if there's a problem that we haven't done in class, I'd be pretty surprised. The idea is that I just look at it and I'm like, this is too big to do all of the side. So I'm just going to split it into two cases. Integral t e minus p of t dt, and then minus integral t squared e minus p minus t dt. Now, when you look at this more carefully, doesn't this look like something we've done in class? They're exactly the same thing we've done in class. Just two of them, basically. So this problem that looked so ugly in the start is literally just a problem we just did probably like 5 minutes ago, and a problem that's one step ahead of the problem we just did 5 minutes ago. So you sometimes gotta just focus on the idea. Like here, you have a t and then some exponential of t. This is a clear by parts again, exactly the same. This is the by parts with t being again. What's the rule? This derivative, this no derivative. Okay. And the same applies here. It's the same thing. I have an exponential and a t squared. No derivative for my choice of parts. Okay, just be sure. Derivative. For parts. Okay, I'm already here. And if you do that, the problem just dies in probably like, I don't know, 7, 8 lines, something like that. But I'm just saying, if you see an ugly formula, invest 1 minute to see if it's actually simpler and it's just like a masquerade for it. Okay? Same for the limit, same for everything in this path. Eventually everything boils down to something simple that we've learned. But yeah, I can do this by parts now, but I'm basically just repeating everything that I've done for ages. So, yeah, just, we're probably just gonna end it here. And, good luck on the mandatory assignment. And next week we're doing a differential equation, which is the last topic I'm gonna cover, and just undercover integral.